My name is Louis Finney. I'm going to be presenting today on JEDI, Joining Encryption and Delegation for IoT. This is based off a presentation by Kumar et al. From the University of California, Berkeley. They contributed to this and came up with this paper, and I'm here to analyze it for my computer security class, COSC 5360 at Marquette University. So I want to start today talking about why this problem is important. So the first thing is that there's a real explosion of IoT devices that have been going on for the past few years now and will continue to do so. So IoT devices encompass everything from like our laptops to our phones to small devices like Raspberry Pis to Fitbit sensors and stuff wearables, all the way down to like temperature sensors in a room. And so there's a wide variety of system architectures used, and so you need a way for all these systems to communicate and have it be encrypted. The problem is that our current forms of end-to-end encryption aren't really suited for IoT. There's just way too many devices for a proper key delegation and management scheme to be used. The focus of this presentation today is going to be on the design decisions that went into JEDI and why JEDI is best suited for building or city IoT systems, very large scale things. So basically, the first design decision made is to decouple senders and receivers. This is pretty standard in IoT right now, so this wasn't a difficult design decision, but they made this because they wanted to avoid a central authority that creates a single point of failure. What I mean by this is if a sensor sends encrypted data using a symmetric key to a server, it's decrypted there, then encrypted again and sent over to me. And that means that if somebody compromises the server, they have access to everyone's data and all the sensors' data, and that would be really bad. So by decoupling senders and receivers, it allows for the messages that are encrypted on device in sensors to then end up in my app or phone still encrypted with that same key. How is this done? It's based on URIs and publish subscribe systems. So you can't have a single like device know who to send the message to for everybody. What you have is this publish and subscribe system. So if we look at our diagram here, we see that this occupancy sensor publishes to this file path. This is URI, Uniform Resource Indicator. So then I can subscribe to that same file path so that I am collecting data from there. It's still done on a server, but it's encrypted on the server and never decrypted until I access it. So before I go on, I want to talk about one of the most critical things that's applied in JEDI, and that's the encryption scheme Wicked IBE. So Wicked IBE is basically a way to generate keys pretty easily and then delegate them out. And so this is done using pattern matching and wildcards. So if we take a look at the diagram on the right, we have this key called K1, and it has this URI pattern, foo, bar, bos, and then a wildcard. It can fill in that wildcard and delegate that to key K2. So that means that anything encrypted with K2 can be decrypted by K1. This combines a couple different resource hierarchies for this, and so it can use the URI and the time. It also provides an extended signature scheme. This is important because asymmetric encryption is really expensive, whether that's Diffie-Hellman or public-private, and that realistically cannot be run on small-scale IoT devices. Even Raspberry Pis can be done, but this is just a better method and a more universal one that can be used on any device. So getting back to the design decisions, we have to talk about decentralized delegation. So first, that allows the system to actually scale and be used in a very custom way depending on the business. So let's take a look at the diagram on the right here. So we have a root that hands out a key to building A, and that building manager can then delegate to different people like a lab director, hey, you have access to the entirety of floor 2, and it also comes with an expiration date. Then that lab director can delegate to Alice, hey, you have access to all the IoT stuff in your office until August 2019. Note that the dates never surpass the ones before it. So August 19th is always before this key, and this key is always before this one. That's going to become important later on. But this combines two different aspects of the hierarchies. The URI, so that's the Uniform Resource Information. That's the file path we talked about earlier, so you can see it down in the diagram. We have soda, and then room, and then a bunch of wildcards. That can then be delegated to soda hall, room 410, and light 0. This is pretty important because no single participant can see all delegations, so it allows for a lot of privacy for the user. And also all the total number of keys ends up being logarithmic rather than having to have symmetric encryption keys based on every device in Alice's office be given to the campus manager or building manager or lab director and then Alice herself. So the next big challenge with JEDI is resource constraints. It needs to run on all of these different types of devices that vary widely in processing power, in memory, and just power supply. So you need to be able to have the same method of encryption on all of these devices. How do you do that? It uses a hybrid system. So we talked about Wicked IBE earlier. That is used to set up encryption for all the devices. So on a sensor, a Wicked IBE encryption scheme would be used once an hour to set up that symmetric key. That symmetric key is then delegated out to the proper recipients. And that's actually the most expensive part of the system in terms of time and power. It draws a lot of energy in order to do that encryption. You need this encryption on device to prevent man-in-the-middle attacks or a gateway compromise if somebody actually has access to the resource. So I know it may seem weird to say, hey, temperature sensor, why do we need to encrypt that on device? That's not that big of a deal, but think of it closer to being a smart home device. So a Ring doorbell, you do not want someone to be able to hook into there and set up some system where the video feed goes to some other address other than the person who is using it. I was curious about this part of JEDI in that it seems like because of how the symmetric key is set up based on the URI, so where it's being encrypted to and the time, I was curious as to if this left open the possibility of a seed attack, but the authors didn't really address it. So the next two big things are integrity and anonymity. We want the integrity of data, we want the integrity of the publisher, and of course we want users to be able to anonymously access their subscriptions. Integrity of data and publisher are achieved using encryption that we talked about previously, using signatures. That one's pretty simple, but because of the decentralization of the system, verifying anonymous signatures, which seems like an oxymoron, is really difficult. Normally, there's a problem with larger sizes, which gets into our resource constraints, but also it's unclear if these things are truly anonymous. And since Wicked IBE is based on patterns, though, the signature for a pattern has the same distribution regardless of the key used to generate it. So that is one thing that allowed for anonymous signatures to be done. But this is one part of the paper that I had problems with, in that it really glosses over this sort of huge issue and doesn't really get into the design decisions that are, okay, if we create a hugely decentralized system, who can authorize things? Revocation of access. So you need a way for users to stop being able to access data to their subscriptions. The best way to do this, and the paper is very clear about this, is to just set short limits of access. So we talked earlier about how there's a time limit. So based on date, it's best to use those in short periods like a week or 2 weeks at most. But let's say something happens and a person is fired and they need to have their access revoked to all their resources immediately. That becomes really difficult. The only way to do it is based on the subtree broadcast system. So if someone's node key has been taken away, all the other leaves here on the right side are also taken away. That is a problem because it gets into, okay, now you're taking away access for a bunch of users, but also this conflicts with another design decision that was made. You can't have both anonymous signatures, so you don't know who's accessing something, and the ability to revoke access to something because you need to know who's trying to access it. This is probably the biggest issue with the paper. There's still some work that can be done in terms of trying to mend these two concepts that don't seem like they would go together at all. But they do seem optimistic that there is a way to mend these two. All right, so enough about the design decisions. Let's talk about how they actually applied and tested this. So they used it on BW2, which is a smart home system used in large buildings right now. They first implemented it in the Go programming language and then was able to break that up into different architectures. So they used 3 different computers to test this system. The x86-64 Intel i7 laptop, that's pretty standard. An ARM 64 Cortex A53 Raspberry Pi, so that gets down to a little bit smaller, right in the middle of how powerful these devices are going to be. And then finally, an ARM 32 Cortex M0 Hamilton sensor with only 32 kilobytes of RAM. I'm seriously impressed that they were able to do this. They were able to apply this actually really easily because JEDI can be used on top of already existing IoT systems. But the main question they needed to answer was, is the battery level sufficient on a Hamilton sensor for it to last a couple of years? Because if it doesn't, then it doesn't really make much sense to implement it this way. All the design decisions were focused on, hey, we need to have a lightweight encryption scheme that doesn't take up a lot of battery life. That's why they had to only create a new key once an hour instead of more frequently. And so let's see how they did. So first, let's focus on the least busy chart. So that's down here. So they encrypted it in 3 different ways: attribute-based encryption, which is similar to Wicked IBE, just a more heavyweight version of it; JEDI, which is the hybrid encryption scheme; and then AES, which is symmetric key only. So that in that AES only, that means that the symmetric key is given to the device at the beginning and then is decrypted on a server, encrypted again, and then is sent to the user. And so we can see if it's attribute-based encryption every time, the battery life is like less than 150 days. It's not long enough. JEDI, you get a little over 3 years, and for AES, you get a little over, just around 5 years. So 3 versus 5 years, based on the design decisions to make it decentralized, this would certainly fit the criteria of successful. You see in this figure 7, so they encrypted and published messages and received and decrypted messages, and they measured the time based on a bunch of different methods. So they have the standard BW2, which is not encrypted, JEDI using an anonymous signature, and trusted key servers. You can see that it's way more expensive to decrypt a message of 1 millibyte, but also there is a noticeable jump each time. You can see here for JEDI Anon signature first message and JEDI first message, it takes a bit more time. But if we look at the scale, we sort of put things in perspective. For encryption, the highest it gets to is probably around 70 milliseconds to encrypt and publish. And for decrypting, it only gets to about less than 20 milliseconds to actually decrypt it. Thank you. This was a really interesting paper to read and analyze. If you have any questions about the paper or want to learn more, you can actually access it here on USC NIX's website. Thank you.